we're going to go ahead and start looking at derivatives. And we're going to start by taking a look here at this graph y equals x squared and trying to find the slope at 2. So real quick before I get into that, this is just the very first thing on derivatives we're doing. So derivatives are tied very closely to slope. I mean, they're almost a synonym of one another. And coming into a calculus class, you definitely have talked a lot about slopes with lines. Okay, so you can tell the slope of a line whether it's positive or negative. This is a positive slope, and if it's steeper or not. So this is a steeper line than that line. So that means this line has a the slope is greater than that slope. Here's an example of a line with a negative slope. But one thing with lines is they're always a constant slope. They're always the same for the whole entire line. So with calculus, what we're going to be able to do is we're going to look at a function that is is curvy, like for instance y equals x squared, and the slopes of that change at every value. So you can see on the left-hand side of this graph, the slopes are negative. The right-hand side, the slopes are positive. Certain places the slopes are not very steep. Certain places they're very steep. So it's a constant changing slope, and we want to try and be able to figure out how can we find the slopes of this function at various points. Okay, so that's kind of what we're starting out with. That's our thought process. So we're going to start out with trying to find the slope on y equals x squared at the point 2, 4. Okay, so that's just it's as good a point as any. Okay, now when we are trying to find the slope of this, I'm going to draw something right now that's called a tangent line to the graph at this point, just so we can kind of see what the slope looks like at this point. Okay, so the tangent line, what that is a line that touches our graph only at this point, at least locally. If you go out far enough, this graph might curve and it could hit it. But in this area, it just touches the graph once and has the same slope. So you kind of think it just goes flush up against the graph at that one point, and that's what a tangent line is. So I haven't drawn this perfect, but it should be close enough for our purposes here. So we're trying to figure out the slope of the graph at this point, which is the same thing as saying to figure out the slope of this tangent line right here. So what I'm going to do is I'm going to start with approximating. Okay? So what we know is we know lines. We know how to find the slope of the line. So we're going to use that to our advantage. And I'm going to start with approximating what this slope might be. So I'm going to pick a point close by. Let's say we pick a point at 3, 9. So we'll say this is the point at 3, 9 right here. And what I'm going to do is I'm going to draw a line between this point at 3, 9 and this point at 2, 4. And I'm going to use the slope of that line as an approximation of the slope that I want. Now clearly it's not exactly the same, because the green line you can see is not the same slope as the black line, is a little steeper. Okay, but let's see here, the green line, if I look at the slope, it's going to be y2 minus y1, 9 minus 4 over 3 minus 2, x2 minus x1, so it'll be 5 over 1, which is just 5. So that's the slope of the green line. So I could say, oh, that's approximately maybe what my slope is. Now I can tell that my slope is definitely less than that, okay? And that really isn't a great approximation. It looks off by quite a bit. Let's think, how could we do a better approximation, okay? What if we choose a point closer to 2, 4? So how about at 2.5, for instance? So the point there at 2.5, it's 2.5, 6.25, so you just figure that out by plugging 2.5 into your function to find the y value. So let me try and draw this tangent line right here. Let's see what that looks like now. I'm sorry, it's not a tangent line. I'm going to draw the line between the point at 2.5 and the point at 2. Let's see what happens. So what I'm hoping you can see here, and I know it's not too easy to see because watching a little video, but you have this blue line that ended up being, that the steepness of it ended up being in between the green line we just found the slope for and the line we're looking for. So what we did is we got a slope that is closer to the slope that we want. So again, up here you have your green line that's steepest, the blue line is a little less steep, and then we have our actual slope, which is even a little bit less steep than that. But we're getting closer. Okay, so let's see what the actual value of this is, this blue line. So it would be y2 minus y1, 6.25 minus 4 over x2 minus x1, 2.5 minus 2. If I subtract that, it's 2.25 over 0.5, and if I divide those, that is going to be 4.5. So the slope of my blue line is 4.5, so that's a better approximation than the green line. Now, I could keep getting closer, like I could maybe choose a point at 2.1. That would probably be pretty darn close. Or I could even get closer than that and maybe choose a point at 2.01, and that would be very close. But we want to find the actual slope of that, so I'm hoping that what you're getting at here is you can see that this point that I first chose at 3, I then chose at 2.5, and then I said I could continue to get closer and closer, and each time I get closer would be more accurate. We're looking at something with limits here. Okay, we want to bring this point infinitely close to this point 2,4 and make a tangent line from there. Alright, so that's what we're going to do here next. Alright, so let's go ahead here, just kind of draw another sketch of this, and I know this sketch is not necessarily to scale or perfect, but it's just for reference. For y equals x squared. So again, we're still trying to find the slope at the point 2,4, but instead of picking a specific point close by, I'm going to pick a general point close by. Okay? So for instance, what if I call this point A? It's at the x value A, so that means its y coordinate, if I plug A into the function, would be A squared. Okay? So what I'm going to do here, and let me just draw my tangent line again real quick here, just so we can kind of get a visual of what the slope looks like that we want. That's the slope that we want. Clearly you can see where I chose that point A, where the point is right now. That slope, if I draw that, as with before, you can see it's clearly not perfect by any means. It's not exactly what we want. But here's the deal. As I mentioned a second ago, we want to bring this point closer and closer and closer and closer to 2, because as we, right now, we start out at the green line, and I hope you can see this, but as I move this point closer and closer to 2, what will happen is that line that connects those 2 points will become more and more and more and more like that actual slope of the line that we want. So if we go infinitely closer to 2, then we should get the exact slope. Okay? So here's what I'm going to do. I'm going to set this up as a I'm going to find the slope of my green line here. So it's going to be y2 minus y1, so it's a squared minus 4 over x2 minus x1, a minus 2. And then I'm going to go ahead and I'm going to find the limit of this as a approaches 2. Technically, since I've set this point on the right, it could be as a approaches 2 from the right if you wanted to put that. But it's not going to really affect the outcome of our answer, because I could have easily chosen a to be on this other side, and so from the left to right it's going to be the same thing. But now the reason I said as a approaches 2, because I want this value a to get this point right here, I want to bring this infinitely close to this other point. Because as I do that, as the points get closer together, the line that I draw between those 2 points gets closer and closer to this actual value, and if I get infinitely close, it will become that actual value of that slope of the black line. Okay? So that's why I did the limit as a goes to 2. Now, from your limit stuff, you can tell that if you just plug 2 in, you get 0 over 0, which tells us that we can probably manipulate, and in this case we can factor out. So I will end up factoring a minus 2 times a plus 2 over a minus 2. So those are going to cancel, so it leaves me just with the limit as a approaches 2 of a plus 2. At this point I can now plug 2 in for a, and I end up getting 4. So we found that the actual slope of 2, or the actual slope of y equals x squared at x equals 2 is 4. Okay? This is the limit of a plus 2, equals 4. That's almost looks like at 2. It's a plus 2. But what we found again was that the limit of our function y equals x squared at 2 is equal to 4. Now, if you wanted to know what the slope was at x equals 3, you could do basically the same thing. You would just use the point 3, 9, and again a squared and set up another limit thing. If you had another function such as x squared minus 3x and you wanted to find the slope at 5, again, you could do the same type of thing. You just have to, I would have to be careful how to set it up so that it's factorable. But, those types of things would work out. Now, something that we would like to be able to do, though, is, in this case, how we just did this, we would have to rework this out. If for y equals x squared, we would have to rework this out for every single value of x. If you wanted to know what the limit was for x equals 5, you'd have to redo that process. If you want to